Hello, this is the last topic of the science of motion, stage 2, which is the law of universal gravitation. It consists in the law of universal gravitation. It is important to note that Newton discovered gravity in 1665. I like this image that says how people fixed light bulbs before Isaac Newton invented gravity, which is funny because before 1665, light bulbs didn't exist, but okay. The gravity is the force of nature that attracts mass to another mass. At this point, we have all been attracted to someone, and the same thing happens with the objects. During class, I told you that it is not the same gravity on Earth as on the moon. I told you that maybe your weight it could be lower at moon in comparison at the weight you have on Earth. Okay, the gravity's force is relative to the distance between two masses. Let me show you. In this PET simulator, which is named is Gravity Force Lab Basics, we can manipulate the mass of the circles. We can move the distance. We can change the distance. We can change the distance, and as you can see, even if the distance is different or one of the masses is higher than other, the force that mass 1 exerts on mass 2 is equal than the force that mass 2 exerts on mass 1. It doesn't matter its size. Nothing else matters about this. This can be explained by the law of universal gravitation, which states that any two bodies attract each other with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between them. This might not be relevant with small objects, but it is very useful to study movement of celestial bodies or very big objects or places on the earth. This is the formula that we will be using. F means force of gravitational attraction, which is measured in newtons, as you can see in this part. The gravitational constant that has a constant value. The mass of object 1 multiplied by mass of object 2, and the distance between objects, which must be squared. Maybe it can be something weird that the distance is represented by an r. This is because when we measure the distance between celestial bodies, we are taking into account the radius, because the radius is at the center of the circle or the body, and you are considering it seems like you are considering the center of this body. Okay, that's why we use the letter r. The law of universal gravitation needs a constant g, which is the gravitational constant. This is the number that you must use to solve some of these problems. This number would always exist. It is constant. It won't change no matter what. Okay? The law of universal gravitation helps us to find gravity in a lot of places. The attraction is mutual between bodies. The weight of a body on the Earth's surface is equal to the gravitational attraction force between the body and the Earth. These bodies are separated by exactly the distance between their centers, which is the same thing I explained you using this image and using the simulator. As you can see, the simulator start measuring the force by using the center of the masses because we are considering the radius. We are using the radius. We can find gravity in other planets or in another Earth places or another places which are far, far away from the Earth's surface, like in a spacecraft, let's suppose. For example, if you want to find the gravity on Mars, you just only have to use the gravitational constant. Let me copy and paste it here. Ready. Okay. If we want to find the gravity on Mars, we just only need the gravitational constant, which is the same we have here, the mass of the planet, and um, the radius of the planet. In some cases, we we could be interested about what's the gravity on certain at certain point of Earth because we know that there are very high places. Let's solve some problems. Find the weight of an astronaut who is on a spacecraft orbiting 250 kilometers from Earth's surface. If their mass is 90 kilograms and the mass of the Earth is 5.976 times 10, 10 to the 24th power kilograms, and the Earth's radius distance is 6.371 times 10 to the 6 power meters. Remember that the weight is a force, okay? And we must find the weight of an astronaut. Since the astronaut is not at Earth, we must first find the gravitational acceleration at the height at which he is located, because he's not on Earth. Therefore, the gravity won't be the same because it is outside our planet. In our planet, the gravity is 9.81 meters per second square. We just only substitute, substitute or replace, I think it's a better word, replace the data inside this formula, in which g is the gravitational constant, which must be multiplied by the mass of the Earth, and then you must add the distance of the Earth, taking account its radius, and add the distance, the height at which this person is located. All of this distance must be squared. Then the gravity at that point is 9.09 meters per second square. Now you have the gravity, which is the acceleration. You have to replace in the weight formula, which is weight equals mass times gravity, or the mass of the astronaut is 19 kilograms and the acceleration is 9.09 meters per second square, and our final answer will be 818.23 newtons. There's another problem. Remember that we can find any gravity value at Earth. There are some places at Earth in which the gravity could be lower because they are far, far away from the center of the Earth, and they are at a high level, taking into account the sea level. If we are at a beach, which are places that are very near from the sea level, the height is very could be very little. But let's suppose you are at the top of the Mount Everest or Mount Fuji. It is desired to know the value of gravity at the peak of Mount Everest, which is located at a height of 8,850 meters above sea level, and the mass of the Earth is the same one as we saw before. We must use this formula that includes the gravitational constant, the mass of the planet, the radius of the planet, and the height, and which is we compose the total distance that must be squared. Okay, we must only replace the data, and we can find our final answer, which is 9.77 meters per second square. As you can notice, this is not a very different result from the gravity that we have on Earth. But remember that since the Mount Everest or some mountains are far from the center of the Earth, the gravity can vary a little bit. Finally, the law of universal gravitation helps to give a fundamental theoretical basis to other theories that studies the universe, like the Kepler laws. Those laws were empirical statements for the understanding of kinematics of planets. So all the places that we cannot see because we are on Earth. In summary, the gravitational force can be measured using this formula. All sorry, this formula. All people have been attracted to someone at some point of their lives, and it will always be true because we will always be attracted by the gravitational force. Don't forget it. Thank you so much. Goodbye.